Hello, in this tutorial I am going to demonstrate how to perform the buckling analysis of thin plates in SAP 2000. Suppose you have this square plate ABCD of thickness 2 mm whose edges BC and AD are loaded uniformly of equal intensities, and suppose the edges AB and CD are free from any loads. These are the degrees of freedoms allowed at each of these four edges. So for example, edge BC is allowed to translate in the X and the Y direction, and it is also free to rotate about the X axis, whereas its rotational and translational degrees of freedom about the remaining directions are restricted. So you go to SAP, create new model. I have set these newtons. We will create grids. So we require two grid lines, each along the x-axis as well as the y-axis, and only one along the z-axis, and the length is 100 mm. Click OK. So to model the plate, we will be using another element which is called the area element. You can select it from here. Just span it over the created square grid. Likewise, like before, we are going to now define the section properties. So there are three types of sections. We will be using shell section, and we are going to modify its properties. So in within shell also there are two types, shell thin and shell thick. You can know about all these properties of different types by looking at the SAP analysis reference PDF which comes with the software. So the material is steel, but its thickness we have to change. It is of thickness 2 mm. Just click OK. Now we are going to assign the defined area section to this element. Now we are going to define the load patterns. So I would like to have a live load. Let me call it as live dist for live distributed. We do not want the dead load pattern, and I would also like to now define the buckling load case. So it corresponds to the live load pattern, and this is the default name, and we are interested in finding, suppose, the first 6 buckling modes. Click OK. Now we are going to uh, assign the loads and the boundary conditions. For SAP, there is a disadvantage that you cannot apply an ideally uniform load to an edge of the area element, and neither you can apply an ideal boundary condition to you cannot apply a continuous boundary condition. So what you can do at most is you have to discretize it. So that is what I'm going to do. First you select the area element, then go to edit areas, divide areas. Let me divide it along the x and the y directions into 20 equal parts. Click OK. So once this is done, I can now apply the boundary condition in the loads. Let me first apply the boundary conditions. Go to assign joints restraints. So we do not want its translation about the z along the z axis, and we do not want its rotation about the z axis and the y axis. Similarly, I can assign the boundary conditions corresponding to these nodes. In this case, we do not want its rotation about the x-axis. Now we can apply the loads. So you select, I'm going to apply the loads at those nodes. So let me apply a load of uh, minus 1 Newton, that is 1 kilonewton of force along the negative y direction. Similarly, let me apply the same loads in the positive y direction at those nodes. Now I can set the analysis options. So in solver options I will select buckling, and I will set the load cases. So I need not run all of them, I need to run only the buckling one. So everything is set. Now I can run it. will ask me the name of the file. So model 6. So you can see this deformed shape corresponds to the first mode, and we have a load factor here of value 2.985. So this means that 2.985 times 1 kilonewton of force at each of these nodes at the top and the bottom has to be applied to make this plate buckle in the first mode. So in all we have a total of 19 points. So 19 times this quantity, which roughly comes out to be 57 kilonewton, it has to be applied in compression to make the plate buckle in the first mode. As you can take a look at its other buckling mode shifts also. So let me also show you the animation corresponding to the first mode. Similarly, I can show you the animation corresponding to the second mode. And the animation corresponding to the third mode. So depending on your requirements of the different types of boundary condition and restraints, you can perform the SAP buckling analysis. I hope this was sufficient. Thanks.